In this video, we're going to take a look at how we can use Taylor's theorem that we described in the last video to kind of apply to a specific function so we can get a sense of how this theorem actually works. So let's take a look at example 1 on the next page. Consider the function f of x, which is equal to e to the x. Okay. Right away, I'm going to go ahead and I'm going to kind of draw a picture out here just so I kind of know what it is that we're working with. So let's suppose I have a nice little graph of e to the x. Okay, so there's my f of x function on my xy axes. And gosh, that is a terrible looking set of axes. But good enough. Okay, so supposing that I have this right here, this is my function. I want to approximate or I want to use an appropriate Taylor polynomial of degree 2 to find a good estimate for e to the first power. Okay, so this is actually a question that comes back from like 6.1. This isn't even a 6.4 question. I'm interested in just trying to create a degree 2 polynomial, so a quadratic polynomial that could estimate e to the first power. So I can see here that maybe at the value of 1, I'm interested in what in the world is the y-coordinate of that point up there. And that might be difficult because I don't know how to plug 1 into e or into e to the x and approximate that maybe without the use of a calculator. But what I can do very, very simply is maybe I could create a polynomial that starts over here at 0. Because I do know exactly what happens over there. So I'll start by saying the following. We will construct a Taylor polynomial centered at x naught being 0. Okay, so that's where I'm going to go ahead and choose to build the polynomial. And if it's going to be a quadratic polynomial, it's maybe no surprise that it might end up looking something kind of like the following. Right? Like, here's a nice little quadratic function. Maybe it looks like this. And so on a short window, it's pretty easy to see these guys are pretty close. In fact, even at 1, maybe these things are pretty close to being the same. This would be p2 of x. So I want to find that formula for p2, and again, that shouldn't be too terribly difficult. Remember that in general, our formula for one of these polynomials will always be the following. Say here, we want p2 of x, and I know that that's always going to be equal to f of 0 plus f prime of 0 times x to the first plus f double prime of 0 over 2. Remember, that's 2 factorial x squared. This is the basic formula. I'm using that formula that we discussed back in section 6.1 to try to go ahead and construct this. So if I was to go ahead and try to simplify this down, let's see, p2 of x, so let's see, if I go to my function and I plug in 0, I get back a 1. If I take the derivative and plug in 0, I still get back a 1. And if I take the second derivative and plug in a 0, I still get back a 1. And so I think I end up with the following polynomial. So this here is the blue polynomial that models the function. And so if I wanted to make a good estimate for e to the first power, instead of plugging 1 into the function, I could plug 1 into the blue polynomial. So I can say e to the first power is the same as going to f and plugging in 1. And that should be roughly the same as going to my polynomial and plugging in 1. And so that would look like plugging 1 in for my polynomial. It looks like I get the value 2.5. So we would guess that e to the first power is roughly equal to 2.5. E to the first is roughly 2.5. Now, if I look at the picture here, this may or may not be a perfectly accurate sketch, because we actually know that the value of e is somewhere closer to like 2.7-ish? 2.72-ish, 71. So it's going to be pretty obvious to see here that we've kind of underestimated this value. But again, it's just meant to provide an estimation. It's a pretty decent estimation. In the picture we can see that my black dot might actually, yeah, be a little bit below what the actual value of e is. But let's suppose for the sake of argument that we never knew what the value of e was. We couldn't go to a calculator and type that value in. We might be interested then in using Taylor's theorem to help us go ahead and measure the size of the gap that exists right in there. How big is that gap? So I want to use Taylor's theorem to find an upper bound on the error of this approximation. 2.5 is not the right answer, so it's got some distance from the right answer. And what might that distance at worst actually be? This is again where Taylor's theorem becomes unbelievably valuable. It allows us to say that the size of the gap will be no bigger than this number, whatever this crunches out to be. So I'm going to try to go ahead and work through each of the individual conditions of Taylor's theorem and then see if we can apply them here. So let's see. The first condition of Taylor's theorem is to say that I need to make sure that I have a function that is going to be differentiable n plus 1 times at my value of x0. So here, our x0 is 0, and our function is e to the x. And so I'll go ahead and start by saying that very obviously, we can note that f of x, which equals e to the x, is actually infinitely differentiable at x0 equals 0, right? Like if I keep taking derivatives of e to the x, I only get e to the x, and I can always plug 0 into that. And I now have to state something else. It's not just good enough that I note that this is infinitely differentiable at x equals 0, because now I have another condition. I need to guarantee that when I'm working on a specific interval containing x0, I'm able to find a value of capital M that satisfies this inequality. So here's what I'm going to do. Taking a look at the picture I have above, I'm going to maybe go ahead and start with this. I want to go ahead and find the error that's going to exist when x is a 1, and I need to create an interval that I'm going to look at that also contains my x0. So here's going to be my interval that I'm going to choose to work with. How about, since I need to include 0 and I need to include 1, I just make my interval 0 to 1. I make this the interval where I'm going to measure or have the ability to measure sizes of gaps. Remember, according to the theorem, I have to have my x0 as a part of my interval, and I also have to have, obviously, whatever x value I want to measure the error at as a part of my interval. So I'm going to choose an interval 0 to 1, and then see if I can find this capital M. So we'll see here that on the interval 0 to 1, we see that, let's see, my n plus first derivative, when absolute valued, I want that to be less than or equal to something. Now for the moment, I'm going to attempt to just simplify it. If I take a look here, I could ask the question, what is the n plus first derivative of e to the x? Well, since I have such an easy function here, that's pretty easy to state. That's just e to the x. Any derivative of e to the x is e to the x. And when I look at the graph of e to the x, if I tried to absolute value it, nothing changes. So this is just e to the x. And now the question is, on the interval -1 to 0, or sorry, 0 to 1, excuse me, on that interval, if I only looked at this portion of the graph right up here, I'm curious, what is a value of capital M that is always equal to or larger than this function? Well, something that I might be able to state maybe right away is that this thing here is definitely always going to be less than e to the power of 1, right? Like e to the 1 is the highest value that this function takes on that interval. But since I don't really maybe know what e to the 1 is, maybe I'll say that this is definitely less than or equal to 3. And so what I'm going to go ahead and do is I'm going to kind of select this value here as my value of m. It's a value that I know exists up here, and I can say that on this interval, 0 to 1, no value gets above that m. No value gets above my 3. So once I have this, I've satisfied the conditions for Taylor's theorem, and I can proceed. So I'll say, by Taylor's theorem, I then know the following. I'm going to go ahead and write down all the different bits of information that I know to fill out what Taylor's theorem specifies. Notice that in Taylor's theorem, if I was to go back and look at it, I'm going to need to know an n, an x, an m, an x0, and I'm going to record all those pieces of information. So here, notice that my x value that I'm approximating my error at is 1. My x naught value is 0. My n value is 2 because I had a degree 2 polynomial. And my m value, we said, was 3. Okay, so I can now go ahead and say, by Taylor's theorem, I know that R2 of 1, so the remainder with the degree 2 polynomial at x coordinate 1, is definitely going to be less than or equal to my value of m over n plus 1 factorial multiplied by the absolute value of x minus my x naught to the power of, n plus 1. So if I look at that, that's 3 over 3 factorial times 1 to the third power. Now that's actually the same as just 1 over 2, right? Because it's going to be 3 over 6, and that's just 1/2. So what I know is that at this particular x value, I know that the size of my gap is at most 1/2. So I'll say the approximation of e to the first being roughly 2.5 is off by at most 1/2. This value of 2.5, according to Taylor's theorem, is at worst case scenario off by 1/2. We know then that the actual value of e is definitely guaranteed to be somewhere from, what, 2 to 3? That would be going down 1/2 and up 1/2 from this approximation. And we actually know that that's perfectly correct because e to the first power should be about 2.7. Now one of the questions that we're going to have is, how could I begin to improve this approximation? Because while it's great to say, hey, this approximation is only off by this much, that still doesn't give me maybe a lot of certainty that I have a great approximation. So right now, the only thing that we can guarantee for sure is that, like, well, I guess like this 2 seems pretty decent, right? At least fairly close to being decent. It's this decimal point that might change based on the amount of error that might be in existence. So these are some very standard questions. In fact, I'd almost go ahead and ask you right now to try to go ahead and start to take a look at some of the worksheet questions where I ask you to do some of these similar sorts of things, and maybe see if you can try to practice some of those. In the next video, we'll take a look at example number 2, where we'll try to flip this question around and see if I wanted to approximate e to a certain amount of accuracy, how big of a polynomial, what degree would I need to have that polynomial take on?